Let's look at how to implement all the cases of interp now that we take a store and we need to return a result. So in the int e case, the simplest case we have, we used to just return an int v right away. And that's still true. Interpreting an integer doesn't change the store at all. So all we have to do is return that integer along with the same store that we started with. So we use the res constructor to make a result with the int v value and stow as the store. IDE is similar. We do what we used to do, which is the lookup, pair it together with the store, because merely looking up a name, a variable in the environment, does not change the store at all. The plus e case does need to change more significantly. We've looked at this, where we used to have num plus and 2 calls to interp. Now we need to use this sequence where we interpret the left with the current store, get back a new store, interpret the right with that new store and get an even newer store. Along with values for the left and right, we're going to add the values together, just like we always did, and return now the latest version of the store. That is, after we return the summed numbers, we want to remember everything that happened as we interpreted L and R, and that information is in this stow R result. Molt is going to be the same, so let's move on to boxy, which is the new and interesting part. A box expression has a sub-expression that provides the initial value to go inside that box. Since this A is an expression, we should interpret it, and since it's the first thing that happens inside of a box C, we use the store that we're given. That's the current store. When we interpret A, we're going to get a result. It's going to have a value for the expression A, which could be anything, and maybe along the way of interpreting this expression, some other things happen to the store. So we need to pay attention to this new store now and not try to use the old one anymore. In this new store, we're trying to create a new box that has the value v. So where does that new box live? We need to allocate a box somehow. So let's wish that we had a new location function that takes a store and gives us back an address that's not currently being used. We can just look through the store and find some number that's not available. So let's say new loc gives us that back. And let's bind that to the name L here. So L is the location for the newly allocated box, and we want to return that as box VL. Right? So this will record the result that box C produces a box V, and L is the address of that new box. Meanwhile, inside that address, we want to put the value V. So we create a cell mapping the location L to the value V, and then we add that to the store that we currently have, the stow V, with override store, and that gives us our new store. So we have our new value and our new store. We put the two together just using res like that. And that's the complete implementation of boxy to allocate a new box with an initial value. Except that we still need to implement this new helper function, new location. New location we implement by finding the max address that's currently in the store and add 1 to it. So if no addresses are allocated, we should get back a 0. Otherwise, we'll get the biggest number used so far. And so 1 beyond that is an unused address so far. Max address just walks over the store to find the biggest location that's mapped already, returning 0 if none are mapped. Let's move on to unbox. So an unbox expression has a sub-expression. Of course, we want to interpret this sub-expression. And what we're expecting back in this case is a value that is a box. Right? So we use match to first pull apart the result, which has a value and a store inside of it. And then we look specifically at that value to see if it's a box V. If it's not a box, we're trying to unbox a number or a function, then we just complain with a not a box error. But if it is a box, then what we get is a location. That is the location where the box produced by A lives, and so we can look in that location to extract the value out, and that's what unbox is supposed to do. We need a new helper function, fetch, which takes a location and a store to look in and gives us the value inside the store at that location. And if we get that value back, that's exactly the value we need to return, except that, of course, we also need to return a store, and stow V is the latest store, so that's the one that we should return. That's the implementation of unbox, as long as we implement fetch. And then setBox is related in the sense that it has a sub-expression bx that we should interpret and expect a box back, but setBox has another expression val that we should interpret to get a new value to put in that box. This is similar to left and right in an add, and that we need to do these in an order. So we interpret the box, with this initial store, we get a new store back in addition to a value for that box. And then we interpret the value with a stow v to get the latest store that we have at the end here, this stow v. So we've got a value that should be a box from the bx expression, a value that can be any kind of value from the val expression, and we have the latest store. We need to make sure that vb is in fact a box. We can match on it to see if we get a box v. If not, we complain. Otherwise, now we have the location where the existing box lives, and what we want to do is change that location in the store to use the result of val. That is, we want to change L to have VV inside it. So that is creating a representation of a cell at L with value VV and override whatever is currently in the store at that location using override store. So this is our new store. We've said that our set box here in Mo is just going to return the same value that we installed inside the box. So that means we have res VV with the updated store, and that's the implementation of setbox. Finally, we have begin. Begin's job, remember, is just to evaluate two expressions in sequence, and we ignore the value from the first one and return the value from the second one. We could do this similar to plus e and multi, but we take a little shortcut here, because after we interpret the left expression and get an updated store, we ignore the left value, but we don't ignore the left store, because the point of evaluating L is to have some effect on the store normally. So we want to use that new store and interpret R, but we don't have to match on this and pull it apart because the result from R is exactly the result from begin, so we can just return it directly like that.